Welcome to Chapter 2. Welcome to 2.1. Welcome to 2.1.1. So big picture, where we're at in Chapter 2 is we're going to talk about first order systems. And really Chapter 2 just parallels Chapter 1. Chapter 1 was an introduction. We started by talking about modeling. We talked about qualitative analysis, numerical analysis. We talked about or numerical approximations. We talked about analytic solutions. Well, that's all Chapter 2 is as well. We're going to start with modeling. That's 2.1. We're going to do some analytic solutions. That's like 2.3 and 2.4. We're going to talk about qualitative analysis. That's 2.2. There are numerical solutions in 2.5, but we're not really going to cover that. So again, like it's really just Chapter 1 again, but now instead of one equation, one variable, it's going to be multiple equations, multiple variables. We're mostly going to be focusing on two equations right now. So we're going to start by introducing this section on modeling with, we're going to revisit that predator-prey system that we looked at a whole chapter ago. I think that's kind of mostly it before I really get started. Yeah, and just remind you all that, again, we have three main ways of dealing with differential equations, but we have to still make the differential equation. Sometimes that's the most interesting, sometimes that's the most difficult, sometimes that's the most important, oftentimes it's the most important part is creating the models, the actual modeling, which is what this section focuses on. So we'll do some analysis here. We're certainly not going to solve anything, and we'll do some hand wavy things and say, people are using Euler's method here, but not us. All right, so let's reintroduce this predator-prey model. So again, we could say R is the population of some predator. Maybe it'll be prey. And F could be some predator, which we could say is foxes. All right, then we could write the relationship. We could say, well, how is the population of rabbits changing over time? Well, there's some growth constant. We're making up some parameters here. There's some parameter for the growth constant. And again, if this is all that this is a very common growth model, right? Is that a population grows exponentially. Here, we have a doubling factor. But we're also saying we lose population depending on how many foxes and how many rabbits there are. The more rabbits there are, the more rabbits can get eaten. The more foxes can eat. They scale multiplicatively. So again, this is some parameter based on how our rabbits and foxes are. And again, it's really any predator-prey model, but it's more fun to think of an actual animals. Or maybe not. Maybe you really like rabbits. I actually do kind of like rabbits. I also like foxes. So anyway, not to get distracted, right? This is saying that, we're losing rabbits. The rate of change has a negative quantity. We're losing rabbits based on how many rabbits and foxes there are. But we also have to model the fox population, right? Well, how are the foxes changing over time? Well, in general, they're not doing great, right? Without the rabbits, the foxes are going to die off. This is exponential decay. And then, of course, we can say, well, there's some good news for the foxes. There's some parameter here that says, well, based on how many foxes and rabbits there are, the foxes are also going to be able to grow. They need rabbits, and they need themselves in order to grow. Rabbits to eat, themselves to reproduce. And again, a pretty simple model. Right? Rabbits are dying from foxes. Foxes are growing because of rabbits. Rabbits will grow exponentially if left alone. Foxes will die out if left alone. All right, so the good news is a pretty simple model. The bad news is it is impossible to solve by hand. Not impossible for you, not impossible for me, impossible to solve by hand. All right, but we can find some solutions. Okay, so let's go over to the next page real quick. Let's look at this, and we're going to find a couple solutions. Oh my gosh, that got very small. I had forgotten I had accidentally zoomed in on the last page. But we'll find a couple solutions. So notably, we can find some equilibrium solutions. Are there any values of rabbits and foxes that will make things zero forever? And of course, you can see there's R's and F's everywhere. If everything's 0, that's an equilibrium solution, right? Is the rabbits are 0 forever, and the foxes are 0 forever. And again, equilibrium solutions in the context of systems of differential equations talk about a pair of solutions or a triplet of solutions. We'll introduce vector notation again, reintroduce vector. Talk about how vector notation can be applied to systems of differential equations, and we'll be using that in the next section. But yeah, this is an equilibrium solution. You may also see this written as the solution 0, 0. R is 0 and F is 0. So that's one solution. What else? What if only one of these is equal to 0 and the other one, can the other one do anything interesting? Well, let's look. What happens if R is equal to 0? What does our differential equation become? dr dt is 0 minus, okay, well, of course, if R is 0, this is 0. Yeah, that makes sense. But if R is 0, how did the foxes look? It's a negative F plus 0. This is still a valid system. Hey, we can solve this system because this one has a solution of just R equals 0. This one has a solution F is equal to some constant, some initial population, e to the negative t. So, okay, we have another solution. 0 comma ce to the negative t. And that makes sense, right? If there's no food, the foxes are going to exponentially die off. All right, so we have a couple solutions. Well, again, let's find another one if the foxes are equal to 0. Similar logic, right? If foxes are equal to 0, this is gone, this is gone. Foxes will always be equal to 0, according to this model, barring any external factors. And the rabbits are going to grow exponentially. Right? So rabbits are going to grow exponentially, some constant, e to the t. And the foxes will be 0 forever. We have another solution of exponential growth. In the next video, we talk about, okay, well, how do we modify this to be logistic growth? And it's actually pretty easy. The solutions get wild, though, which is fun. All right, let's see. Any other things? Oh, yeah, we could factor. If we factor and make things look a little nicer. If we factor, what do we get from our equations? We can factor an R out of the first one. Everything's fine. I'm going to move my light so my cat doesn't knock it over. And if we factor and take out an R, what are we left with? 2 minus 1.2 times F. And if we factor out something from the Fox equation, what are we left with? Negative 1 plus 0.9 times R. And so you can see another another solution popping up. It may or may not be an equilibrium solution, but notice that this equation solved if F is equal to a certain value. And this equation solved if R is equal to a certain value. So we can get an equilibrium solution if R of t, F of t equals, well, if R is just add 1, divide by 0.9, whatever that number is, and if F is, add that, all right, 2 divided by 1.2, then we get another solution. And again, that solution approximates to about, I did this calculation ahead of time, 1.1 repeating and 1.6 repeating, I believe. So we have some solutions here. This is an equilibrium solution as well. Why? Because it's a constant solution. It's a pair of constant solutions specifically. So we have 2 equilibrium solutions and we have 2 other solutions. These, again, are somewhat trivial because they're not very interesting. Why look at a system if one thing's going to be 0? But they are solutions and there's some interesting things that happen. A notable thing for this solution, right, is that if at these values of rabbits and foxes, and again, this is not saying 1.1 rabbits, maybe this is the thousands of rabbits or millions of rabbits, right? It's just some quantity of rabbits. I haven't given you the units here. So, maybe at about 1,000 rabbits, what happens is that the growth rate and the decay rate are actually the same, right? When the rabbits is 1.1 and the foxes are 1.6, the growth rate of the rabbits is 2.2. And the growth rate of the foxes, and the death rate from the foxes is also going to be 2.2 when you multiply it out. And same with the foxes, right? At these values, their growth rate and their death rate are the same. Okay, which is kind of fun. So that's pretty much what we have, kind of in just an introductory thing. A quick comment before we look at some graphs and see the answer is that if we have an initial condition for this, it's going to be a pair of initial conditions, right? I would give you that R of 0 is some R naught, and F of 0 is equal to F naught. If we're trying to solve this differential equation, we need to know how many rabbits and foxes there were at the start. We need both of those. Everything's going to come in pairs now, right? The solutions come in pairs, the initial condition come in pairs, and again, solutions must satisfy not one equation anymore. The pair of solutions must satisfy both equations for all time. Okay, and if we use Euler's method, covered in 2.5, again, we've talked about one-dimensional Euler's method, but for systems, Euler's method's covered in 2.5. If we use Euler's method, we can generate solutions. And they look not quite sinusoidal, but kind of similar. And so you can see the graph of the rabbits over time for some initial condition. So if we have this initial number of rabbits and this initial amount of foxes, the rabbits will grow, and then they're going to almost die off, and then grow again, and then almost die off, and then you can see periodic motion here. And we get something very, very similar with the foxes. They have different peaks, different troughs. Do they have the same period? We'll answer that in a second. But you can see something very similar. And what's very interesting is if you grab both of these graphs and put them on top of each other. If you put them on top of each other, you can really see what happens, right? The rabbits are growing because there's not very many foxes. But then we reach some critical mass up here where the foxes are saying, like, let's go. There's so many rabbits, the food is great. So the rabbits start dying off and the foxes are growing because they're eating so much. But eventually, right, there's a point where, okay, we ate all the rabbits. And the foxes can't sustain themselves anymore. And the rabbits are still getting eaten, but eventually the foxes die off enough that the rabbit population can start growing again. And you can see that this is going to repeat. This cycle is going to repeat. This cycle, I said, we have periodic motion. They do indeed have the same periods. We can somewhat see that now. We'll be really able to see that if we talk about something called a phase portrait, which we'll introduce in the next video. And yeah, we get a lot of cool stuff over here. This is one way of visualizing a solution to this system of differential equations. It's one way. It's like plotting both solutions over time. They have a relationship. Another way is actually going to be more similar to a phase line. I'm spoiling it. Spoiling the next video, but it's okay. And then as a side note, a little comment, right? This y-axis is showing two things. Rabbits and foxes, they may have slightly different units, so we might need two different labeling for the y-axis, but here we're just going to assume that they have this mostly the same units, just one being rabbits and one being foxes. Okay, so that's kind of an introduction to modeling. Again, important thing to kind of focus on is how does this model make sense? What do each of these terms represent? That's really important. We can get, how do we find some solutions? Here's some different methods of finding some solutions. Finding all solutions by hand is impossible, but we can use a systems analogous version of Euler's formula or not Euler's formula, rather Euler's method to find these approximations, and then we can plot them together. We'll do more about this with this model in the next video. But that's an introduction. Bye-bye.